In 4.2, we're going to talk about two specific things that we need to know about in order that we'll be able to do the rest of the chapter. The first two things that we're going to talk about are these things called perpendicular bisectors. Most of you have heard about this before in Math 1 or Advanced Math 8. What we're going to talk about has everything to do with this perpendicular bisector theorem and its converse. They are specifically stated in Theorem 25 and 26, and they have names. But the property we're going to be talking about is that if there is a point, like point C, on the perpendicular bisector, it is equidistant from the endpoints of that segment that it is bisecting. Meaning, if I know this is on the perpendicular bisector, and I have an endpoint A and an endpoint B, then the distance from C to A is going to be exactly the same thing as from C to B. As a matter of fact, any point on CD is equidistant from point A and point B. Meaning if I had point C right, let's say here, C1, or I had point here, C2. If I had those points, it doesn't really matter if I were to measure from here to there, and let me get another one of those guys. From here to there, as long as I'm going to the endpoints, those are going to be the same distance away. If I were to think about multiple ones of those, here to here, here to here, they are going to be the same distance as each other because of this side is going to be the same in both triangles. The angle is going to be the same in both triangles, and this other side is going to be the same in both triangles. Because of something we learned in Chapter 3, we're going to be able to do a bunch of things with these perpendicular bisectors. That's the whole idea. I hope you see a connection between what we did in 3 and what we're going to be doing here with these perpendicular bisectors. So that's what these two theorems say. The perpendicular bisector theorem, it says do not write because we're just going to read them. And then what we'll do is I'll show you how you're going to do some problems with them. If a point is on the perpendicular bisector of a segment, point P is on the perpendicular bisector, then it is equidistant from the endpoints of that segment. If P is on the perpendicular bisector, then PA must be equal to PB. The converse of that is, if I know that these two segments are congruent to each other, then this point must also be on the perpendicular bisector. It's very cool to know that if I have an isosceles triangle, that the point at the top, the vertex angle, is going to always be on the perpendicular bisector. And we're going to be able to do some proofs with that if we need to in this chapter. Okay? So the first idea, what is a perpendicular bisector? It is equidistant from the endpoints of the thing that's being bisected. The second thing that we're going to do is that we're going to do the same thing except with an angle bisector. An angle bisector is when we cut an angle into two equal measurements. But before we get to that, I need to mention something to you because some people don't understand this and I need to point it out. The distance from a point to a line is measured as the shortest distance. It's always perpendicular to the line. If I say, how far is this point from the line? You don't measure at a diagonal. You don't measure all the way over here. You measure it as the shortest distance possible. Like from here to there. It needs to be at a perfect right angle. If it's not, then you're not measuring it correctly. If I say, how far away are you from Teague Avenue? Teague Avenue goes from Woods Elementary all the way down to Fort Washington Middle School, right by Clovis West. How far away are you from Teague? You're going to measure it as the distance right outside these doors. It's right there. I mean, you're this far away from Teague, the shortest distance, not where Woods is or where Clovis West would be. Okay? Why is that important? Because if I have a point that is on a triangle, imagine that this is a triangle and I have an angle bisector of this triangle, and I have a point that is on the angle bisector, if I say how far is this point D from this side, you always have to measure it as the shortest distance possible, otherwise known as perpendicular. If I'm trying to measure to this side, I don't measure it to B, I measure it as the shortest distance possible, which is always perpendicular. They're equidistant as long as we're talking about perpendicular to the sides of the angle. Which brings us to the angle bisector theorem, which says if a point is on the angle of the bisector of an angle, then the point is equidistant from the sides of the angle. This distance and this distance need to be the same. So if I know this is the same as this, and this is perpendicular and that's perpendicular, then these two pieces have to be congruent. That's the angle bisector theorem. The converse of that is also true. If I know that these are the same as each other and these are measured at a perfect right angle, then what I know is that this has to be on the angle bisector. Otherwise, it wouldn't be true. And if you're wondering why, that's because of HL. HL works on these ones. There we go. So the rest of these things that I have for you are all examples out of your book. If you want to open your book, we're going to do number 5, 12 and 13, and 24. Number 5 says, find the measure of angle KHL and the measure of angle FHL. We're trying to figure out how big this angle is. The first thing that I notice is I have this segment LF, not LF, I'm sorry, this segment here, which is congruent to this segment there, and it's measured at a right angle. If this distance is the same as this distance measured perpendicular to the side, then I could use that angle bisector theorem to know that these two angles must be congruent. The only way that this is going to be congruent to that and have this right angle is that these two pieces have to be the same, which means your computer crashes. Which means that 6y should be equal to the 4y plus 18. And then what do? We subtract the 4y. We divide by 2. We get what y is equal to. And then we always go back and read the question and say, hey, did it ask me to find y? And it didn't. It said find the measure of KHL. KHL is this angle right here. It's 6 times y. So 6 times the 9 means that that angle is 54 degrees. And if I were to do the same thing, if I want to double check my answer, I can plug the 9 in over here and do 4 times 9, which is 36. And we could add 18 to that and see what we get. And I bet you anything, it should be 54 degrees, which means it's an angle bisector and it would be congruent to each other. So those are our two answers. This answer and that answer right there. Any questions? Let's jump to 12 and 13. When I look at this and you see this, it asks you to find x, it asks you to find tw, but before we even do that, I hope you know what this is. What is YW? If you know what YW is, say it out loud. What word is it? Words are they? Is it? Good. It is a perpendicular bisector, if you didn't know. This is a perpendicular bisector because it's perpendicular and those two pieces are congruent. And because it's a perpendicular bisector, the distance from W to the endpoint and w to the other endpoint need to be congruent or the same. So what is the value of x? All we do is set the 2x equal to the 3x minus 5. And you solve it. If you ever subtract something onto the same side, don't forget that's equal to 0. And then what you would have to do is move the 5 to where the 0 side is so that you have what x is equal to. I have x is equal to 5. Is that what you got? Okay, so that's our answer for number 12. And number 13 says find TW. You have to plug it back in to figure out what TW is. 2 times 5 is the value of 10. So we now have the answer to 12 and the answer to 13. Last example, number 24. Determine whether A must be on the bisector of angle TXR. Explain. Is this point on the bisector of angle TXR? When I first read this question, I go, well, it's not measured. I don't know if this is perpendicular. I don't know if these are equidistant to the sides. But then it says this, whether A must be on the bisector. Is this A on the bisector? You can look right here. What do these two things mean? It means that they are congruent to each other. If these are two congruent to each other, then this is an angle bisector. Is it, must it be? Yes, it must. Yes. Angle RXA is congruent to angle TXA. Because these two angles are congruent to each other, AX must be part of the angle bisector, just so you know. I'm going to stop your notes right there.